to experience Rust firsthand. It demonstrates how to use the compiler and then moves on to writing a quick program. We tackle full projects in later chapters. Note: to install Rust, use the official installers provided at rustup.rs. Section 1.3.1 Cheating Your Way to Hello World. The first thing that most programmers do when they reach for a new programming language is to learn how to print Hello World to the console. You'll do that too, but with flair. You'll verify that everything is in working order before you encounter any annoying syntax errors. If you use Windows, open the Rust command prompt that is available in the Start menu after installing Rust. Then execute this command. If you are running Linux or Mac OS, open a terminal window. Once open, enter the following. From this point forward, the commands for all operating systems should be the same. If you installed Rust correctly, the following three commands will display Hello World on the screen, as well as a bunch of other output. Here is an example of what the entire session looks like when running command.exe on MS Windows. And on Linux or Mac OS, your console will look like this. If you have made it this far, fantastic. You have run your first Rust code without needing to write any Rust. Let's take a look at what just happened. Rust's cargo tool provides both a build system and a package manager. That means Cargo knows how to convert your Rust code into executable binaries and also can manage the process of downloading and compiling the project's dependencies. Cargo New creates a project for you that follows a standard template. The tree command can reveal the default project structure and the files that are created after issuing Cargo New. All Rust projects created with Cargo have the same structure. In the base directory, a file called cargo.toml describes the project's metadata, such as the project's name, its version, and its dependencies. Source code appears in the src directory. Rust source files use the .rs file name extension. To view the files that Cargo New creates, use the tree command. The next command that you executed was cargo run. This line is much simpler to grasp, but Cargo actually did much more work than you realized. You asked Cargo to run the project. As there was nothing to actually run when you invoked the command, it decided to compile the code in debug mode on your behalf to provide maximal error information. As it happens, the source/main.rs file always includes a Hello World stub. The result of that compilation was a file called hello, or hello.exe. The hello file was executed, and the result printed to your screen. Executing Cargo Run has also added new files to the project. We now have a cargo.lock file in the base of our project and a target/directory. Both that file and the directory are managed by Cargo. Because these are artifacts of the compilation process, we won't need to touch these. Cargo.lock is a file that specifies the exact version numbers of all the dependencies so that future builds are reliably built the same way until cargo.toml is modified. Running tree again reveals the new structure created by invoking Cargo Run to compile the Hello project. For getting things up and running, well done. Now that we've cheated our way to Hello World, let's get there via the long way. Section 1.3.2 Your First Rust Program. For our first program, we want to write something that outputs the following text in multiple languages. You probably have seen the first line in your travels. The other two are there to highlight a few of Rust's features, easy iteration, and built-in support for Unicode. For this program, we'll use Cargo to create it as before. Here are the steps to follow. 1. Open a console prompt. 2. Run cd%tmp% on MS Windows, otherwise cd$tmp. 3. Run cargo new hello2 to create a new project. 4. Run cd hello2 to move into the project's root directory. 5. Open the file src/main.rs in a text editor. 6. Replace the text in that file with the text in listing 1.1. The code for the following listing is in the source code repository. Open ch1/ch1-hello2/src/hello2.rs. Now that src/main.rs is updated, execute cargo run from the hello2 directory. You should see 3 greetings appear after some output generated from cargo itself. Let's take a few moments to touch on some of the interesting elements of Rust from listing 1.2. One of the first things that you are likely to notice is that strings in Rust are able to include a wide range of characters. Strings are guaranteed to be encoded as UTF-8. This means that you can use non-English languages with relative ease. The one character that might look out of place is the exclamation mark after println. If you have programmed in Ruby, you may be used to thinking that it is used to signal a destructive operation. In Rust, it signals the use of a macro. Macros can be thought of as fancy functions for now. These offer the ability to avoid boilerplate code. In the case of println exclamation point, there's a lot of type detection going on under the hood so that arbitrary data types can be printed to the screen. Section 1.4. Downloading the book's source code. In order to follow along with the examples in this book, you might want to access the source code for the listings. For your convenience, source code for every example is available from 2 sources. manning.com/books/rust-in-action, github.com/rust-in-action/code. Section 1.5. What does Rust look and feel like? Rust is the programming language that allows Haskell and Java programmers to get along. Rust comes close to the high-level, expressive feel of dynamic languages like Haskell and Java while achieving low-level, bare-metal performance. We looked at a few Hello World examples in Section 1.3, so let's try something slightly more complex to get a better feel for Rust's features. Listing 1.2 provides a quick look at what Rust can do for basic text processing. The source code for this listing is in this file. Some features to notice include common control flow mechanisms. This includes for loops and the continue keyword. Method syntax. Although Rust is not object-oriented, as it does not support inheritance, it carries over this feature of object-oriented languages. Higher order programming. Functions can both accept and return functions. For example, line 19 includes a closure, also known as an anonymous function or lambda function. Type annotations. Although relatively rare, these are occasionally required as a hint to the compiler. For example, see line 27 beginning with if, let, OK of length. Conditional compilation. In this listing, lines 21 through 24 are not included in release builds of the program. Implicit return. Rust provides a return keyword, but it's usually omitted. Rust is an expression-based language. Listing 1.2 might be confusing to some readers, especially those who have never seen Rust before. Here are some brief notes before moving on. On line 17, the fields variable is annotated with the type vec of underscore. Vec is shorthand for underscore vector underscore, a collection type that can expand dynamically. The underscore instructs Rust to infer the type of the elements. On lines 22 and 28, we instruct Rust to print information to the console. The println! Macro prints its arguments to standard out, or std out, whereas eprintln! Prints to standard error, or std error. Macros are similar to functions except that instead of returning data, these return code. Macros are often used to simplify common patterns. eprintln! And println! Both use a string literal with an embedded mini-language in their first argument to control their output. The braces placeholder tells Rust to use a programmer-defined method to represent the value as a string rather than the default representation available with these characters. Line 27 contains some novel features. If let OK of length equals fields1.parse of F32 reads as attempt to parse fields1 as a 32-bit floating point number, and if that is successful, then assign the number to the length variable. The if-let construct is a concise method of conditionally processing data that also provides a local variable assigned to that data. The parse method returns an OK of t, where t stands for any type, when it can successfully parse the string. Otherwise, it returns error of e, where e stands for the error type. The effect of if let OK of t is to skip any error cases like the one that's encountered while processing the line invalid, data. When Rust is unable to infer the types from the surrounding context, it will ask for you to specify those. The call to parse includes an inline type annotation as parse of F32. Converting source code into an executable file is called compiling. To compile Rust code, we need to install the Rust compiler and run it against the source code. To compile listing 1.2, follow these steps. 1. Open a console prompt, such as cmd.exe, PowerShell, Terminal, or Alacrity. 2. Move to the ch1/ch1-penguins directory, not ch1/ch1penguins/src, of the source code you downloaded in section 1.4. 3. Execute cargo run. Its output is shown in the following code snippet. You probably noticed the distracting lines starting with dbg:. We can eliminate these by compiling a release build using cargo's -- release flag. This conditional compilation functionality is provided by the CFG !debug_assertions block within lines 22 through 24 of listing 1.2. Release builds are much faster at runtime, but incur longer compilation times. It's possible to further reduce the output by adding the -q flag to cargo commands. -q is shorthand for quiet. The following snippet shows you what that looks like. Listing 1.1 and Listing 1.2 were chosen to pack as many representative features of Rust into examples that are easy to understand. Hopefully, these demonstrated that Rust programs have a high-level feel paired with low-level performance. Let's take a step back from specific language features now and consider some of the thinking behind the language and where it fits within the programming language ecosystem. Section 1.6. What is Rust? Rust's distinguishing features as a programming language is its ability to prevent invalid data access at compile time. Research projects by Microsoft's Security Response Center and the Chromium Browser project both suggest that issues relating to invalid data access account for approximately 70% of serious security bugs. Rust eliminates that class of bugs. It guarantees that your program is memory safe without imposing any runtime costs. Footnote 13. See the articles We Need a Safer Systems Programming Language at this link, and Memory Safety at this link for more information. Other languages can provide this level of safety, but these require adding checks that execute while your program is running, thus slowing it down. Rust manages to break out of this continuum, creating its own space as illustrated in Figure 1.1. Rust's distinguishing feature as a professional community is its willingness to explicitly include values into its decision-making process. This ethos of inclusion is pervasive. Public messaging is welcoming. All interactions within the Rust community are governed by its code of conduct. Even the Rust compiler's error messages are ridiculously helpful. Until late 2018, visitors to the Rust homepage were greeted with the technically heavy message, Rust is a systems programming language that runs blazingly fast, prevents segfaults, and guarantees thread safety. At that point, the community implemented a change to its wording to put its users and its potential users at the center. See Table 1.1. Rust is labeled as a systems programming language, which tends to be seen as quite a specialized, almost esoteric branch of programming. However, many Rust programmers have discovered that the language is applicable to many other domains. Safety, productivity, and control are useful in all software engineering projects. Moreover, the Rust community's inclusiveness means that the language benefits from a steady stream of new voices with diverse interests. Let's flesh out those three goals: safety, productivity, and control. What are these, and why do these matter? Section 1.6.1. Goal of Rust: safety. Rust programs are free from dangling pointers, live references to data that has become invalid over the course of the program. See Listing 1.3. Data races, the inability to determine how a program will behave from run to run because external factors change. See Listing 1.4. Buffer overflow, an attempt to access the 12th element of an array with only 6 elements. See Listing 1.5. Iterator invalidation, an issue caused by something that is iterated over after being altered midway through. See Listing 1.6. When programs are compiled in debug mode, Rust also protects against integer overflow. What is integer overflow? Well, integers can only represent a finite set of numbers. These have a fixed width in memory. Integer overflow is what happens when the integers hit their limit and flow over to the beginning again. The following listing shows a dangling pointer. Note that you'll find this source in this file. Listing 1.3 contains a pointer with grains, which is created on line 8. VAC of serial is implemented with an internal pointer to an underlying array, but the listing does not compile. An attempt to do so triggers an error message that complains about attempting to borrow a moved value. Learning how to interpret that error message and to fix the underlying error are topics for the pages to come. Here's the output from attempting to compile the code for Listing 1.4. Listing 1.4 shows an example of a data race condition. If you remember, this condition results from the inability to determine how a program behaves from run to run due to changing external factors. You'll find this code in this file. If you are unfamiliar with the term thread, the upshot is that this code is not deterministic. It's impossible to know what value data will hold when main exits. On lines 6 and 7 of the listing, 2 threads are created by calls to thread spawn. Each call takes a closure as an argument, denoted by vertical bars and curly braces. The thread spawned on line 5 is attempting to set the data variable to 500, whereas the thread spawned on line 6 is attempting to set it to 1000. Because the scheduling of threads is determined by the OS rather than the program, it's impossible to know if the thread defined first will be the one that runs first. Attempting to compile Listing 1.5 results in a stampede of error messages. Rust does not allow multiple places in an application to have write access to data. The code attempts to allow this in 3 places: once within the main thread running main, and once in each child thread created by thread spawn. Here's the compiler message. Listing 1.5 provides an example of a buffer overflow. A buffer overflow describes situations where an attempt is made to access items in memory that do not exist or are illegal. In our case, an attempt to access fruit 4 results in the program crashing, as the fruit variable only contains 3 fruit. The source code for this listing is in this file. When listing 1.5 is compiled and executed, you'll encounter this error message. The next listing shows an example of iterator invalidation, where an issue is caused by something that's iterated over after being altered midway through. The source code for this listing is in this file. Listing 1.6 fails to compile because Rust does not allow the letters variable to be modified within the iteration block. Here's the error message. Well, the language of the error message is filled with jargon, borrow, move, trait, and so on. Rust has protected the programmer from stepping into a trap that many others fall into. And fear not, that jargon will become easier to understand as you work through the first chapters of this book. Knowing that a language is safe provides programmers with a degree of liberty. Because they know their program won't implode, they become much more willing to experiment. Within the Rust community, this liberty has spawned the expression fearless concurrency. Section 1.6.2 Goal of Rust Productivity. When given a choice, Rust prefers the option that is easiest for the developer. Many of its more subtle features are productivity boosts. But programmer productivity is a difficult concept to demonstrate through an example in a book. Let's start with something that can snag beginners. Using assignment equals within an expression that should use an equality equals test. In Rust, the preceding code fails to compile. The Rust compiler generates the following message. At first, mismatched types might feel like a strange error message to encounter. Surely we can test variables for equality against integers. After some thought, it becomes apparent why the if test receives the wrong type. The if is not receiving an integer. It's receiving the result of an assignment. In Rust, this is the blank type, open close parentheses. Open close parentheses is pronounced unit. Footnote 14. The name unit reveals some of Rust's heritage as a descendant of the ML family of programming languages that include OCaml and F#. The term stems from mathematics. Theoretically, a unit type only has a single value. Compare this with Boolean types that have 2 values, true or false, or strings that have an infinite number of valid values. When there is no other meaningful return value, expressions return unit. As the following shows, adding a second equal sign on line 4 results in a working program that presents A equals 10. Rust has many ergonomic features. It offers generics, sophisticated data types, pattern matching, and closures. Those who have worked with other ahead-of-time compilation languages are likely to appreciate Rust's build system and its comprehensive package manager, Cargo. Footnote 15. If these terms are unfamiliar, do keep reading. These are explained throughout the book. They are language features that you will miss in other languages. At first glance, we see that Cargo is a front end for Rust-C, the Rust compiler. But Cargo provides several additional utilities, including the following. Cargo New creates a skeleton Rust project in a new directory. Cargo Init uses the current directory. Cargo Build downloads dependencies and compiles the code. Cargo Run executes Cargo Build and then also runs the resulting executable file. Cargo Doc builds HTML documentation for every dependency in the current project. Section 1.6.3 Goal of Rust Control. Rust offers programmers fine-grained control over how data structures are laid out in memory and their access patterns. While Rust uses sensible defaults that align with its zero-cost abstractions philosophy, those defaults do not suit all situations. At times, it is imperative to manage your application's performance. It might matter to you that data is stored in the stack rather than on the heap. Perhaps it might make sense to add reference counting to create a shared reference to a value. Occasionally, it might be useful to create one's own type of pointer for a particular access pattern. The design space is large, and Rust provides the tools to allow you to implement your preferred solution. Note: if terms such as stack, heap, and reference counting are new, don't put the book down. We'll spend lots of time explaining these and how they work together throughout the rest of the book. Listing 1.7 prints the line A:10, B:20, C:30, D mutex, data 40. Each representation is another way to store an integer. As we progress through the next few chapters, the trade-offs related to each level become apparent. For the moment, the important thing to remember is that the menu of types is comprehensive. You are welcome to choose exactly what's right for your specific use case. Listing 1.7 also demonstrates multiple ways to create integers. Each form provides differing semantics and runtime characteristics. But programmers retain full control of the trade-offs they want to make. To understand why Rust is doing something the way it is, it can be helpful to refer back to these three principles. The language's first priority is safety. Data within Rust is immutable by default. Compile time checks are strongly preferred. Safety should be a zero-cost abstraction. Section 1.7 Rust's biggest features. Our tools shape what we believe we can create. Rust enables you to build the software that you want to make, but we're too scared to try. What kind of tool is Rust? Flowing from the three principles discussed in the last section are three overarching features of the language: performance, concurrency, memory efficiency. Section 1.7.1 Performance. Rust offers all of your computer's available performance. Famously, Rust does not rely on a garbage collector to provide its memory safety. There is, unfortunately, a problem with promising you faster programs. The speed of your CPU is fixed. Thus, for software to run faster, it needs to do less. Yet, the language is large. To resolve this conflict, Rust pushes the burden onto the compiler. The Rust community prefers a bigger language with a compiler that does more, rather than a simpler language where the compiler does less. The Rust compiler aggressively optimizes both the size and speed of your program. Rust also has some less obvious tricks. Cache-friendly data structures are provided by default. Arrays usually hold data within Rust programs rather than deeply nested tree structures that are created by pointers. This is referred to as data-oriented programming. The availability of a modern package manager, Cargo, makes it trivial to benefit from tens of thousands of open-source packages. C and C++ have much less consistency here, and building large projects with many dependencies is typically difficult. Methods are always dispatched statically unless you explicitly request dynamic dispatch. This enables the compiler to heavily optimize code, sometimes to the point of eliminating the cost of a function call entirely. Section 1.7.2 Concurrency. Asking a computer to do more than one thing at the same time has proven difficult for software engineers. As far as an OS is concerned, two independent threads of execution are at liberty to destroy each other if a programmer makes a serious mistake. Yet, Rust has spawned the expression fearless concurrency. Its emphasis on safety crosses the bounds of independent threads. There is no global interpreter lock, or GIL, to constrain a thread's speed. We'll explore some of the implications of this in Part 2. Section 1.